You already know what time is. You've never had to think about it. It passes, it flows, you feel it. You measure it with clocks, and clocks agree with each other. And that agreement feels like the most natural thing in the universe. Of course they agree. Why wouldn't they? That assumption is wrong, and not in some abstract philosophical way. Wrong in the precise, measured, experimentally confirmed way that science means when it says wrong. But let's not get ahead of ourselves. Let's start with something even simpler. Think about this. You're sitting still right now. A train rushes past you at 100 kilometers per hour. From where you stand, that's obvious. The train is moving. You are not. But a passenger on the train looks out the window and sees you rushing backward at 100 kilometers per hour. From her frame, she's the one sitting still. You're the one moving. Who is right? Both of them. That's the correct answer. And Galileo understood it. There is no absolute state of rest. Motion is always relative to something else. That idea is old. It's not controversial. It's the kind of thing you accept and move on from. Here's where it starts to get uncomfortable. In the 1860s, James Clerk Maxwell wrote down a set of equations describing electricity and magnetism. Those equations predicted something nobody asked for. They predicted that light is an electromagnetic wave, and they told you very precisely how fast that wave travels. Roughly 300,000 kilometers per second. The equations didn't say relative to something. They just said that. One number, one speed, fixed. That should bother you. If motion is always relative, then what is light moving at 300,000 kilometers per second relative to? The train? You standing on the platform? The answer the 19th century gave was relative to a medium, a substance that filled all of space called the luminiferous ether. Light moved through the ether, the way sound moves through air. The ether was the reference point, the thing that wasn't moving, the absolute rest. It was a beautiful solution, tidy, reasonable, wrong. In 1887, Michelson and Morley built an experiment to detect the ether. The logic was clean. If Earth moves through the ether as it orbits the sun, then light sent in the direction of Earth's motion should travel at a slightly different speed than light sent sideways. The difference would be small, but measurable. They built a device sensitive enough to measure it. They ran the experiment. They found nothing. No difference. None. They ran it again. They ran it in different seasons, when Earth was moving in different directions. Still nothing. The ether did not exist. There was no medium. And yet light still had that single precise speed, not relative to anything. Just that speed. Always. That is not an answer. That is a crisis. Here's the strange part. Most people, confronted with this result, assume the experiment must be flawed. The mind wants to preserve what it knows. But the experiment wasn't flawed. The result was real. The universe was telling you something. And what it was telling you was that the speed of light is the same for every observer, regardless of how fast they are moving. Let that land. It doesn't land easily. Imagine you are standing still, and you shine a flashlight forward. The light leaves at 300,000 kilometers per second, relative to you. Now imagine I am on a rocket, moving toward that same beam of light, at half the speed of light. Every instinct you have says I should measure the light coming at me faster. After all, I'm rushing toward it. The relative speed should add up. It doesn't. I measure the same 300,000 kilometers per second. Identical. The speed of light does not add. That is real. It has been measured in particle accelerators, in laboratories, with atomic clocks, with GPS satellites. It is not a theory anymore. It is a fact about the universe. The speed of light is invariant. It does not care how fast you are moving. Now here's where the avalanche starts. If the speed of light is always the same, and speed is distance divided by time, then for the speed to remain constant across observers who are moving relative to each other, either the distances they measure must differ, or the times they measure must differ, or both. Both. Einstein understood this in 1905, not by running experiments himself, but by taking two things seriously: Galileo's principle of relativity and Maxwell's equations. He asked what the world must look like if both of those things are exactly, precisely, completely true at the same time. The answer was that time is not what you think it is. A moving clock runs slow. That is not a metaphor. It is not an artifact of measurement. The clock itself, the physical object, ticks less frequently when it is in motion relative to you. The faster it moves, the slower it ticks. At the speed of light, it would stop entirely, and distances compress. A ruler moving past you at high speed is shorter along its direction of motion than it would be at rest. Not because it's being squeezed by a force, because space itself, measured from your frame, is contracted. This is where your intuition fails, and you have to let it fail. Your brain was built on a planet moving at ordinary speeds over time scales that don't require precision beyond fractions of a second. Your intuition about time was calibrated by evolution, not by physics. And evolution had no reason to show you the behavior of objects at 100,000 kilometers per second. So your gut says, time is time. 1 second everywhere is 1 second. That's just what a second means. That is exactly wrong. There are muons, subatomic particles created in the upper atmosphere when cosmic rays strike air molecules. They are created roughly 15 kilometers above Earth's surface. Their half-life is about 2 microseconds. In 2 microseconds, even traveling at nearly the speed of light, they should cover less than a kilometer before half of them decay. They should never reach the ground. Most of them should be gone long before they get here. They reach the ground. We detect them, thousands of them, every second, passing through your body right now. They survive the trip because from our frame of reference, their internal clocks are running slow. They're experiencing much less time than we calculate they should be experiencing. And this matches the predictions of Einstein's equations precisely, not approximately, precisely. Here's where the original question collapses. You started by asking, how fast is something moving? That question has a perfectly sensible answer, but buried in that question is an assumption that time is a fixed backdrop against which things move, that the universe has one common clock, that simultaneity is absolute, that 2 events either happen at the same moment or they don't, and every observer agrees. That assumption is the problem. It is the wrong picture from the beginning. Space and time are not separate. They are aspects of a single structure called space-time. What is space to one observer is a mixture of space and time to another. When you move through space, you rotate in space-time. And what we experience as the passage of time, as the ticking of clocks, as the aging of bodies, is movement through the time dimension of that structure. The universe doesn't have a rule that says keep time constant. It has a deeper rule. Something called the space-time interval must be preserved. The geometry of space-time is rigid. Every observer measuring every event must agree on the space-time interval between those events, even if they disagree on the time and disagree on the space separately. The interval is what's real. The universe adjusts time and space individually for every observer to keep that deeper structure intact. That's not a bug. That is the design. The question, what time is it, really, is not a question that has a universal answer. And that is not a limitation of our instruments. It is a fact about reality. The original question was incomplete. It assumed that really had a frame-independent meaning. It doesn't. This isn't philosophy. We have tested it. GPS satellites orbit at high speed and at high altitude, which means 2 effects. Special relativity slows their clocks due to velocity. General relativity speeds them up due to reduced gravitational potential. These effects are small, but not negligible. If you ignored them, GPS positioning would drift by roughly 10 kilometers per day. The engineers account for both corrections. The system works to centimeter precision. Every time you navigate somewhere with your phone, you are using Einstein's geometry. The Large Hadron Collider accelerates protons to within a fraction of a percent of the speed of light. The physicists there must account for relativistic mass and time dilation in their calculations, not as curiosities, but as engineering constraints. The math works. The collisions happen where and when the equations say they will. And here's the uncomfortable truth at the end of this. The universe is not required to be intuitive. It is not obligated to conform to what a 3-pound human brain expects after spending its life among slow-moving objects on the surface of a medium-sized planet. The universe has a structure. It is precise, it is consistent, and it is beautiful in the way that deep mathematics is beautiful. But it does not owe you comfort. What Feynman understood and kept insisting upon was this: the job is not to explain why the universe feels sensible. The The job is to ask what is actually true, take the answers seriously, even when it is disturbing, and then follow it wherever it leads. That is how we got here. Newton noticed that the same force pulling an apple pulls the moon, and that was enough to describe the orbits of planets. Maxwell wrote down 4 equations about fields and got light as a consequence. Einstein took 2 principles seriously and dismantled absolute time as a side effect. Each discovery didn't close a door. Each one opened the next room. Quantum mechanics is the next room. And in that room, the ideas become more unsettling still. Particles with no definite position. Measurement that changes what is measured. Entanglement that produces correlations across arbitrary distances. All of it tested. All of it confirmed. The chain keeps going. It has not ended. Every answer so far has contained the seed of the next question, and the pattern does not suggest the chain will stop. That should not comfort you. It should fascinate you. There is a difference.